So we have an array of n distinct integer, uh, and we have to sort this array using a star search. The action consists of swapping two different numbers, okay, and each action costs 1 unit. And the goal state is the sorted array, and because this is a star search, we need some heuristic. The heuristic for heuristic, a variable is defined as. Now this as is the total number of misplaced digits in the array. For example, let's say an initial array of 3 digits, 0 to 1. The S value of this will be 2, as 2 and 1 are misplaced and 0 is in its correct place. Now we have to find all possible children of this array. This will be nc2, n being the number of digits, and therefore because the digit is 3, it will be 3c2, 3c2 being 3. So the possible children of this node will be 201, 120 and 012. Each action costs 1 unit, okay. So let's see the S value of 201. 201 will have S value of 3, as all three digits are misplaced. The delta S is the difference between the parent node and this current node. So this will be 3 minus 2, 1 plus 1. The second children is 120. Its S value is also 3 because all three digits are misplaced. Delta S will be plus 1 as well. If we swap the last two digits, the S value is 0 because this is our sorted array. So there is no misplaced integer. Delta S will be minus 2. See, it went from plus 2 to minus 2. If it went plus 2 to 0, and therefore delta S being minus 2. We have to find something, right? So to solve this question, the thing you need is what is the maximum amount by which we can reduce S in one action. So what can be the maximum value of delta S ever? This will be, we'll find how to so to find this, we have to consider all possible, what are the all possible things that can happen to a number when we do this an action. Now there are two possibilities. Whether or not first possibility is that number is not the one being swapped of that this number we have choose, random number we choose, is not in the one of the two digits which are being swapped in this array, or it can be that this number is being swapped in one of those possibility. Now let's say if this is not if this is not being swapped, then the delta S will be 0 for that digit because its position is not being changed. Now for the numbers being which are for the digit which is being swapped, it could be in its correct position already, or it could be in its wrong position. If it's in the correct position, it cannot be swapped to another correct position because there is only one unique correct position. So if the digit is already in its correct position, delta S for that digit will be plus 1. And let's say that this digit is in its wrong position. Here whether it could be swapped to a correct position or it could be swapped to another incorrect position. If it is swapped to another incorrect position, delta S will be 0 because nothing essentially has changed for that digit. It was in the wrong position, it's still in the wrong position. But if it swapped to a correct position, delta S will be 1 because the one digit which was previously misplaced is now correctly placed. Since we talked about this for one digit, right? So since in a one swap, two digits are being changed, so the maximum possible value of delta S will be minus 2, as in one swap we could have corrected two misplaced digit. So what is the maximum amount by which we can reduce S in one action? It is 2. Now let's say it takes K action to go from a start state to goal state via optimal path. Here Sk will be 0 as we took this action, and the goal state, the S value of the goal state is 0 as there is no misplaced digit. Okay, and for optimal path, each action should reduce S by its maximum amount, that is 2. Why? Because if it does not, we will need some more actions required, so it will not be an optimal path. So the minimum amount of action to reach start state to goal state is K. Okay. So after k action, the sk is the s value of the state in which we are in after k action. Okay, so s of 1 will be s minus 2, because in one action we are reducing s by 2, so s1 is equal to s minus 2. In two action we will reduce it by another 2, so s minus 2, s minus 2. In k action we will reduce it with 2 times k, so sk is equals to s minus k times 2. And since the value of sk is 0, because in sk we are already at the goal state, right, and goal state has s value of 0, so 0 equals to s minus 2 times k. And here we can find by adding 2 times k on both sides of the equation, we can say s is equal to 2 times k. Now we have to like, what is the definition of admissibility? Definition of admissibility is that the heuristic cost of each node must be less than the real optimal cost. Okay, optimal cost being the cost which we have when we go from start state to end state, no, from via optimal path. Okay, now c is 1 times k. Why? Because the cost is 1 unit times the number of action taken. Because the cost of each action is 1, so the total number of action is k, because we use in the optimal path, the total cost will be 1 times k, which is k. So hn, which is this heuristic function, must be less than equal to k. Let's say hn is m times s, m being some variable, a random variable, I don't know, some variable, and s is the as previously defined. Now hn equals will be m times s, so ms will be less than equal to k. Now we can do some algebra to figure out the all possible values of m. The all possible values of m, ignoring the negative values, because negative heuristic doesn't make sense, will be 0 to 1 by half inclusive. So we can put various values of m and find the all possible answer. If the value of m is 0, we will get the last D option correct. If the value of m is 1 by 3, we can get the C option correct. And if the value of m is 1 by 2, we can get the second option correct. But you see, the value of m cannot be 1, right? So first option is not correct. Thank you. If you have any other problems, let me know in the comment section.